So this week, we are going to talk about one special type of linear programming problems called transportation problems. So what is transportation problem? A transportation problem seeks to minimize the total shipping cost of transportation goods from some location to other locations. So before we start, let's look at the graphical illustration for a transportation problem that aims to ship items from 2 origins to 3 destinations. As you can see in this network illustration, each origin node has a capacity or supply constraint. And we will use a superscript I to denote the supply availability at node I. In this transportation problem, we want to ship the items from the original nodes to satisfy the demand at each destination node. And again, we will use D subscript J to denote the node J's demand. So basically, we want to find the amount to ship from each original node to each destination node. In order to formulate the problem, we will use index I to denote the original node. Similarly, index J is used to indicate the destination node. And the unit shipping cost from node I to node J is denoted by C subscript ij. For example, the cost of shipping 1 unit of the item from the first origin node to the first destination node is C11. And the cost of shipping 1 unit of the item from the second origin to the third destination is C23. So with the network representation on hand, we are ready to see how we can solve the transportation problem as a linear programming problem to find the optimal solution about the number of units to be shipped from each origin I to each destination J, in order to minimize the total shipping cost while satisfying all supply and demand constraints. So let's first define the decision variables. We first let X subscript ij represent the number of units to be shipped from origin I to destination J. As you can see, the first index is the origin index, and the second index is the destination index. We can see that the shipping cost for shipping Xij items from the I's origin node to the J's destination node is C subscript ij times X subscript ij. Therefore, the total cost is the sum of the shipping cost between each origin and destination combinations as shown in the objective function, and the goal is to minimize the total cost. This optimization problem is subject to 3 different types of constraints. The first one is the supply constraint. That is, we need to make sure that each original node has a supply limitation such that the total amount of the item that are shipped out of that original node cannot exceed the total amount of the supply. In these equations, the left-hand side is the sum of all quantities that are shipped out of node I, and the right-hand side is the total supply available at node I. Each node I will have a supply constraint. If we use the network example in this slide, there will be 2 supply constraints, one for original node 1 and the second one for the original node 2. The second type of constraint is the demand constraint. Each destination node has a demand constraint such that the total amount of the items that are shipped to the destination node should satisfy the demand. The left-hand side of the demand constraint is the sum of all quantities that are shipped into the destination node, and the right-hand side is the particular destination node's demand. In this slide's network illustration example, because there are 3 destination nodes, so we will have 3 demand constraints. Finally, we include the non-negativity constraint for the decision variables. If we do not include the non-negativity constraint, it is possible to get a solution that involves negative numbers, whereas the amount of items to be shipped from one node to another should be non-negative. The formulation shown in this slide is the general formulations that can be applied to any number of origin and any number of destination nodes. So now let's try to apply this formulation idea to a more concrete transportation problem. We can first draw a network representation for this problem. There are two origins, plane 1 and plane 2. And we also have three destinations, northward, westward, and eastward. The unit delivery cost for each origin and destination combination is in the table, and we can map these numbers to the network representation. Now, let's start with the first component of the linear programming formulations, which is the decision variables. Let's define Xij to be the tons of concrete block to shift from plane I to destination J. Remember to indicate how the index to the locations.
In particular, I equal to 1
represent plane 1, and I equal to 2 represent plane 2, and J equal to 1 represent northward, J equal to 2 represent westward, and J equal to 3 represent eastward.
And J equals to 3 represents eastward.
As the second step, we want to write down the objective function. We will ship X11 tons concrete block from plane 1 to northward, and it costs $24 to ship 1 tons of concrete block from plane 1 to northward. Therefore, the delivery cost for shipping X11 tons of concrete block from plane 1 to northward is 24 times X11. Similarly, the delivery cost for shipping X12 tons of concrete block from plane 1 to westward is 30 times X12. Using the same logic, we can write down the delivery cost between each plane and destination. We add up all the costs for each origin and destination to get the total delivery cost. And the goal is to find the best Xij values to minimize the total delivery cost, subject to the supply, demand, and non-negativity constraints. Next, we want to list all constraints. There are three types of constraints: supply, demand, and non-negativity. We start with the supply constraint. There are two original nodes, so there will be two supply constraints. The supply constraint for plane 1 is that the total amount to be shipped out of plane 1 cannot be more than the amount that is available in plane 1. Therefore, we can write the constraint as X11 plus X12 plus X13 less than or equal to 50. The left-hand side X11, X12 plus X13 is the total quantity to be shipped out of plane 1, and this total quantity should be less than or equal to 50 tons, which is the supply at plane 1. Similarly, we can write down the supply constraint for plane 2 as X21 plus X22 plus X23 less than or equal to 50. Where the left-hand side of the equation is the total quantity that will be shipped out of plane 2. And this total amount should be less than or equal to plane 2 supply, which is 50 as well. After we write down the supply constraint, we can move on to list all the demand constraints. There are three destinations, so there will be three demand constraints. The demand constraint for Northwood is that the total amount of concrete blocks that are shipped to Northwood should cover the demand of 25 tons. We can see that the Northwood concrete blocks can come from Plan 1 or Plan 2, or both. The total quantity to be shipped to Northwood is X11 plus X21, and this quantity should equal to 25 tons to cover the demand. Similarly, the demand constraint for Westwood is X12 plus X22 equal to 45. And the demand constraint for Eastwood is X13 plus X23 equal to 10. Finally, don't forget to include the non-negativity constraint for the decision variables. We include the non-negativity constraint to ensure that feasible solutions are positive numbers, as we do not want a solution that will ask us to ship a negative quantity of concrete blocks. Now, we have the complete linear programming formulation of the problem, and we can use Excel solver to find the optimal solution. Next, I would like you to try an example on your own. This problem may not exactly like shipping items from some origins to some destination at the first glance. But if you look closely, you will see that we can use the same logic to formulate the problem. First, let's define the decision variables xij as the pounds of materials to be shipped by mode I to destination j. Second, we can write down the objective function as to minimize the total shipping cost. Third, let's list all the constraints. The supply constraint says that regulation requires equal distribution of shipping among the three transportation modes. The Navy needs to deliver 9,000 pounds of the material with these three transportation modes. Therefore, the Navy needs to deliver 3,000 pounds of the material using each transportation mode. Then, we include the demand constraint for each destination. Finally, we include the non-negativity constraints. Once we have the complete formulation for this linear programming problem, we can use Excel solver to solve the problem. The optimal distribution plan is available in the next slide.